March 15th, 1945. Iwo Jima, Airfield No. 2, newly captured by American forces after 36 days of the bloodiest fighting in Pacific War history. Captain Saburo Kitahata of the Imperial Japanese Navy watched through field glasses as mechanics pushed the damaged F4U Corsair into a makeshift hangar constructed from salvaged corrugated steel and wooden beams. The fighter's distinctive inverted gull wings were scorched from flak damage, its massive propeller bent from the forced landing 3 days earlier. But the aircraft was largely intact. The first operational Corsair the Japanese had recovered in flyable condition during nearly 3 years of devastating aerial combat. The irony was not lost on Kitahata that this intelligence windfall had come to them on an island where over 21,000 Japanese defenders had died fighting American forces, equipped with the very technology they were now examining. Every piece of equipment surrounding them, from American bulldozers that had carved the airstrip from volcanic rock to the P-51 Mustangs that patrolled overhead, represented industrial and technological capabilities that seemed to mock Japan's increasingly desperate situation. Within the crude shelter, Lieutenant Commander Jiro Horikoshi, chief designer of the legendary Zero fighter and arguably Japan's most brilliant aeronautical engineer, knelt beside the American machine with a measuring tape borrowed from a construction crew. What he was discovering would shatter every assumption Japanese aviation held about climb performance, engine power, and the fundamental limitations they believed governed all fighter aircraft. The numbers emerging from his calculations were impossible. According to his measurements and analysis, this American fighter could outclimb a Zero at 20,000 feet, a claim so preposterous that senior officers would demand he verify his findings 3 separate times. Horikoshi had spent the last 4 years watching his creation, the Mitsubishi A6M0, transformed from the world's premier naval fighter into an increasingly obsolete machine being systematically destroyed by American pilots in superior aircraft. The psychological burden was immense. He had created a fighter so successful in early 1942 that it achieved near-mythical status, enabling Japanese naval aviation to dominate Pacific skies from Pearl Harbor to Ceylon. Now, in March 1945, that same fighter was being shot down in ratios approaching 15-1 by American aircraft that seemed to violate every principle he had considered fundamental to successful fighter design. The story of how Japanese pilots came to possess this Corsair, and what they learned when they refused to accept its performance capabilities, reveals the moment when Japan's aviation establishment confronted the true magnitude of American engineering achievement. Through systematic testing and grudging acknowledgement, they would discover that their most fundamental beliefs about fighter design were not just wrong, but catastrophically inadequate for the technological war they were fighting. The capture itself had been almost accidental, a stroke of fortune amid unrelenting disaster. Lieutenant Robert Mackenzie, of Marine Fighter Squadron VMF 214, had been conducting his 3rd strafing run of the morning against Japanese positions on northern Iwo Jima when concentrated anti-aircraft fire from concealed positions damaged his R-2800 engine. A 25mm shell had punctured his oil cooler, while shrapnel from nearby bursts had severed fuel lines and damaged control cables. Trailing thick black smoke and losing oil pressure rapidly, Mackenzie had perhaps 2 minutes of engine power remaining. The 23-year-old pilot from Oklahoma had faced similar situations before, during his tour with VMF 214. This was his 47th combat mission, and he had already shot down 3 Japanese aircraft while supporting the grueling ground assault on Iwo Jima. But this time, geography worked against him. The nearest American-controlled airstrip was USS Saratoga, operating 30 miles offshore, too far for a damaged aircraft leaking oil and fuel. Mackenzie made the decision that would inadvertently provide Japanese aviation with its most valuable intelligence opportunity of the war. Rather than attempting to reach friendly territory, and almost certainly crashing into the ocean, he chose to belly land on relatively flat volcanic sand near Japanese defensive positions. His wheels-up landing was expertly executed, with the massive Corsair sliding over black sand for nearly 200 yards before coming to rest largely intact. Mackenzie escaped from his aircraft and evaded Japanese patrols for 6 hours before being rescued by an American reconnaissance team. but his fighter remained in enemy hands. The recovery operation mounted by Japanese forces demonstrated the value they placed on captured American equipment. Despite constant threat from American air attacks and artillery bombardment, a team of engineering personnel and mechanics spent 12 hours moving the downed Corsair to concealed positions using improvised equipment. They worked primarily at night, covering the aircraft with camouflage nets during daylight hours when American fighters patrolled continuously overhead. Captain Kitahata arrived on Iwo Jima specifically to evaluate this captured aircraft. As one of Japan's most experienced test pilots, with over 3,000 flight hours in dozens of different aircraft types, he had been ordered to examine captured enemy equipment throughout the war. His previous assignments had included flying captured P-40 Warhawks recovered in the Philippines, examining wrecked B-25 bombers shot down over Japan, and studying fragments of P-38, Lightnings recovered from various Pacific battlefields. But never had he possessed an intact, modern American fighter representing the cutting edge of enemy technology. The opportunity was extraordinary, but the timing was ominous. By March 1945, Japan's strategic situation was hopeless in every measurable category. American B-29 bombers were systematically destroying Japanese cities in massive incendiary raids that killed hundreds of thousands of civilians. The Imperial Navy had been effectively eliminated as a fighting force following disasters at the Philippine Sea, Leyte Gulf, and countless smaller engagements. Japanese merchant shipping had been reduced to coastal traffic, with American submarines having sunk over 5 million tons of cargo vessels. Most critically for aviation, Japan's pilot training programs had collapsed under fuel shortages and accelerated graduation schedules. New pilots reached operational units with fewer than 100 hours of flight time compared to American aviators who received over 400 hours of training before entering combat. The qualitative gap in pilot training compounded technological disadvantages to create nearly insurmountable odds for Japanese aircrews. Captain Kitahata, an experienced test pilot with over 3,000 flight hours, had been ordered to evaluate captured enemy aircraft throughout the war. He had flown captured P-40 Warhawks, examined wrecked B-25s, and studied fragments of P-38 Lightnings. But never had he possessed an intact, modern American fighter representing the cutting edge of enemy technology. The opportunity was extraordinary, but the timing was ominous. By March 1945, Japan's strategic situation was hopeless, making this intelligence-gathering exercise more academic than operational. The Corsair sitting before him represented an F4U-1D, incorporating 3 years of combat refinements since the type's troublesome debut at Henderson Field, Guadalcanal, in February 1943. Its massive Pratt & Whitney R2800 double Wasp engine, producing over 2,000 horsepower at takeoff power settings, dwarfed the Nakajima Sakai 14 radial powering the Zero. The American fighter weighed 14,670 pounds fully loaded, compared to the Zero's 6,025 pounds, nearly 2.5 times heavier. It carried 6 50-caliber Browning machine guns with 2,350 rounds of ammunition compared to the Zero's mixed armament of 2 20mm cannons and 2 7.7mm machine guns with approximately 1,000 rounds total. Most significantly, it possessed comprehensive armor protection that Japanese fighters had largely abandoned in pursuit of performance and range. The armor installation alone revealed fundamentally different design philosophies. The Corsair incorporated 150 pounds of armor plate protecting critical areas, the pilot's seat and back, the engine firewall, and oil cooler. The windscreen featured bullet-resistant glass nearly 1.5 inches thick. Self-sealing fuel tanks incorporated multiple rubber layers designed to swell when punctured, preventing catastrophic fuel loss from battle damage. Japanese fighters had experimented with similar protection early in the war, but had systematically removed it to save weight and improve performance. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To Japanese eyes, the Corsair represented everything wrong with American fighter philosophy. It was heavy, complex, expensive to build, and required extensive maintenance infrastructure. Japanese design doctrine, codified through years of resource constraints and strategic necessity, emphasized lightness, simplicity, and operational efficiency above all else. The Zero's phenomenal range of over 1,900 nautical miles and extraordinary dogfighting ability had dominated Pacific skies in early 1942 precisely because Japanese engineers had stripped away everything deemed unnecessary for achieving air superiority. This design philosophy reflected broader Japanese military thinking about resource allocation and strategic imperatives. Japan's industrial capacity was severely limited compared to potential enemies, particularly the United States. Japanese planners understood they could not match American production in terms of quantity, so they pursued qualitative advantages through superior design efficiency. Every pound of weight saved, every unnecessary component eliminated, every simplification implemented represented precious resources that could be applied elsewhere in Japan's overstretched war economy. The Zero embodied this approach perfectly. Mitsubishi's design team, led by Horikoshi, had created a fighter that could outrange any contemporary opponent while maintaining superiority in the critical performance areas of climb rate, turning ability, and service ceiling. The aircraft's aluminum construction used the minimum material necessary to achieve structural requirements. Its Nakajima Sake engine was reliable, fuel-efficient, and relatively simple to manufacture and maintain. Control surfaces were fabric-covered to save weight. The landing gear was fixed to eliminate complexity. Every design decision prioritized operational effectiveness over durability or pilot protection. This philosophy had produced spectacular results in the war's early phases. Zero fighters had achieved air superiority from Pearl Harbor to Ceylon, destroying hundreds of Allied aircraft while suffering minimal losses themselves. The fighter's 3,200-mile range enabled operations across the vast Pacific that no other aircraft could attempt. Its climbing ability and maneuverability allowed Japanese pilots to dictate engagement terms against heavier, more powerful opponents. The aircraft seemed to validate Japanese design philosophy completely. However, by 1945, the strategic context had changed dramatically. American industry had mobilized fully, producing fighters that incorporated sophisticated technologies Japanese engineers understood theoretically but could not manufacture reliably. More critically, American pilots now possessed extensive training and combat experience that eliminated the qualitative advantages Japanese aviation had relied upon. The tactical situation had reversed completely, with American fighters achieving kill ratios that approached 15-1 in many engagements. Experienced Japanese pilots reported scenarios that seemed to violate basic principles of aerial combat. American fighters could climb away from engagement at will, using superior engine power to escape before Japanese pilots could respond effectively. They could dive away from combat faster than Zeros could follow, disappearing into clouds or distance before Japanese aircraft could close range. Most frustrating, American fighters could absorb battle damage that would destroy Japanese aircraft, continuing to fight effectively despite hits that should have been decisive. Yet Japanese aviation leadership refused to acknowledge that fundamental design philosophy might be flawed. The institutional commitment to lightness and efficiency had become dogma that prevented objective analysis of changing combat requirements. When American fighters began dominating Pacific combat, Japanese experts assumed the problem lay in pilot training deficiencies, tactical mistakes, or numerical disadvantage, anything except basic design inadequacy. Lieutenant Commander Horikoshi found himself in an impossible position. As the Zero's principal designer, he bore responsibility for an aircraft that had achieved legendary status in Japanese military thinking. The fighter's early success had made him one of Japan's most respected engineers. However, he also possessed the technical knowledge necessary to understand exactly why his creation was being systematically destroyed by American opponents possessing superior technology. The Zero's early success had created institutional blindness to evolving combat conditions. Between December 1941 and mid-1942, Japanese pilots flying Zeros had achieved air superiority throughout the Pacific theater. The fighter's combination of range, maneuverability, and climbing ability seemed to validate Japanese design philosophy completely. American pilots in P-40 Warhawks, British pilots in Brewster Buffaloes, and Dutch pilots in various obsolete fighters were consistently outfought by Zero pilots who could choose engagement terms through superior aircraft performance. This success bred overconfidence that persisted long after tactical conditions had changed fundamentally. As American industry began producing advanced fighters with powerful engines, sophisticated systems, and superior high-altitude performance, Japanese aviation continued pursuing design approaches that had succeeded earlier. The institutional commitment to traditional priorities prevented recognition that aerial combat was evolving beyond Zero capabilities. By 1943, American fighters like the F-6F Hellcat and F4U Corsair were demonstrating performance characteristics that seemed impossible according to Japanese understanding of aerodynamic principles. These aircraft were heavier than Zeros, carried more equipment, and incorporated systems that Japanese designers considered unnecessarily complex. Yet they consistently outperformed Japanese fighters in combat, achieving superior climb rates, diving speeds, and high-altitude capabilities, despite their apparent disadvantages. The cognitive dissonance was severe. Japanese engineers could measure American aircraft weights, calculate wing loadings, and analyze power-to-weight ratios that suggested inferior performance. Yet combat results indicated exactly the opposite. American fighters were winning through capabilities that Japanese analysis suggested they should not possess. Either Japanese understanding of aerodynamic principles was fundamentally flawed, or American engineers had solved problems that Japanese aviation had not even recognized. Examining the captured Corsair forced a different conclusion that would challenge every assumption Japanese aviation held about modern fighter design. Horikoshi's initial measurements revealed an aircraft built to manufacturing standards that Japanese industry struggled to achieve even under peacetime conditions. The massive Pratt & Whitney engine represented a masterpiece of precision manufacturing, with internal tolerances measured in thousandths of an inch and surface finishes that approached jewelry-quality craftsmanship. The propeller assembly, 13 feet 4 inches in diameter and weighing over 400 pounds, was the largest ever fitted to a single-engine fighter, requiring the distinctive inverted gull wing design to provide adequate ground clearance. The propeller itself revealed sophisticated engineering that Japanese manufacturers could not duplicate. Hamilton Standard's hydromatic variable pitch system incorporated internal mechanisms with dozens of precisely machined components operating in hydraulic fluid under extreme pressures. The blade angles could be adjusted continuously during flight to optimize performance for different phases of operation: fine pitch for takeoff and climbing, coarse pitch for high-speed cruise, and even reverse pitch for landing deceleration. Japanese propellers were fixed-pitch wooden designs that represented a compromise for all flight conditions, optimized for none. Most shocking to Japanese observers was the overall build quality that permeated every aspect of the aircraft. Individual components, from major structural elements to small fasteners, showed manufacturing precision and material quality that exceeded anything in contemporary Japanese fighters. American aluminum alloys possessed superior strength characteristics achieved through metallurgical processes Japanese industry could not consistently replicate. Surface finishes were smoother and more professional throughout the aircraft. Welding quality was uniform and precise. Even paint application showed attention to detail that Japanese factories, operating under wartime pressure and resource constraints, could no longer achieve. These observations reflected fundamental differences in industrial approaches that extended far beyond individual manufacturing techniques. American aviation production emphasized standardization, precision tooling, and quality control systems that ensured consistent results across thousands of aircraft produced by multiple contractors. Components manufactured in different factories fit together perfectly because dimensional standards were maintained through sophisticated measuring equipment and statistical quality control. Japanese production, constrained by resource limitations and increasingly decentralized manufacturing to avoid bombing attacks, struggled to maintain uniform standards even within single factories. The implications were staggering when considered at scale. American industry was producing thousands of fighters monthly with quality that exceeded Japanese laboratory standards. Each Corsair represented approximately 140,000 individual parts, manufactured by contractors across dozens of states, coordinated through supply chains that never seemed to experience shortages or delays. Japanese aircraft production struggled to maintain quality with substitute materials, conscripted workers, and factories operating under constant threat of air attack. But these manufacturing observations, impressive as they were, did not explain the Corsair's reported performance advantages that seemed to contradict fundamental principles of aeronautical engineering. Japanese pilots throughout the Pacific consistently reported that American fighters could outclimb Zeros at medium and high altitudes, escaping combat through superior vertical performance that should have been impossible given their greater weight and complexity. The Zero's light construction and large wing area should have provided decisive climb advantages according to basic aerodynamic principles. Elementary physics suggested that lighter aircraft with lower wing loading would outclimb heavier fighters carrying additional equipment and armor. Yet, combat reports indicated exactly the opposite. American pilots routinely used superior climb performance to dictate engagement terms, attacking when advantageous and escaping when threatened, leaving Japanese pilots unable to force decisive combat. Captain Kitahata decided to resolve these contradictions through systematic flight testing, despite the obvious risks involved. The captured Corsair represented an unprecedented opportunity to examine American fighter capabilities under controlled conditions, but conducting such tests required extensive preparation under extremely difficult circumstances. The aircraft's engine had suffered damage during Mackenzie's forced landing, primarily from flying debris that had punctured the oil cooler and damaged several cylinder heads. Japanese mechanics, working with improvised tools and limited spare parts, had spent weeks fabricating replacement components from salvaged materials. Oil cooler tubes were repaired using techniques developed for maintaining Zero fighters. Damaged cylinder heads were welded and remachined using manual equipment. The supercharger system required extensive cleaning and adjustment after saltwater exposure during the initial recovery operation. Fuel presented another significant challenge. The Corsair required 100-octane aviation gasoline, which Japanese forces possessed in extremely limited quantities. Most Japanese aircraft operated on lower-octane fuel that would not provide full power from the R2800 engine. Kitahata had managed to acquire sufficient high-octane fuel for approximately 4 hours of flight testing, enough for basic performance evaluation, but insufficient for comprehensive analysis. The testing program would need to be carefully planned to maximize information gathered during limited flight time. Kitahata developed a systematic approach, focusing on the most critical performance parameters that could be evaluated using improvised measurement techniques. Climb performance could be assessed by timing ascents to various altitudes. Maximum speed could be estimated through carefully timed runs over measured distances. Diving characteristics could be evaluated through controlled descent profiles. Maneuverability could be compared directly with Zero performance during mock combat exercises. Most importantly, the high-altitude capabilities that seemed to give American fighters decisive advantages could be tested directly. Japanese pilots consistently reported that American fighters maintained superior performance above 20,000 feet, while Zeros became increasingly ineffective as altitude increased. If these reports were accurate, the Corsair should demonstrate measurable performance advantages that would explain American tactical dominance in high-altitude combat. The testing location presented additional complications. American air superiority over Iwo Jima was virtually complete, with carrier-based fighters conducting continuous patrols that made any flight operations extremely dangerous. Japanese radar stations had been destroyed early in the battle, leaving defenders blind to approaching aircraft. American pilots, seeing a Corsair airborne near Japanese positions, might reasonably assume it was an enemy aircraft attempting to escape and attack accordingly. Despite these risks, the intelligence value justified proceeding with flight tests. Understanding American fighter capabilities might provide insights that could improve Japanese tactics or influence future aircraft development. More importantly, the systematic analysis would either confirm or refute combat reports that seemed to contradict established aerodynamic principles. On March 22, 1945, conditions finally permitted the first test flight. Weather was marginal, with broken clouds at 8,000 feet, providing some concealment from American patrols. Kitahata had positioned observers at various locations around the test area with accurate timepieces to record performance data. Emergency landing sites had been identified in case of mechanical problems. Fuel consumption would be monitored carefully to ensure sufficient reserves for safe landing. The first flight would focus on basic handling characteristics and climb performance to 10,000 feet. If the aircraft performed satisfactorily and no American fighters intervened, additional testing could be conducted during subsequent flights. The opportunity was extraordinary, but the window was limited. American ground forces were advancing steadily across Iwo Jima, and the makeshift test facility would inevitably be overrun within days or weeks. On March 22, 1945, Kitahata made his first flight in the captured Corsair. The experience was immediately revealing. The American fighter accelerated faster than any Japanese aircraft he had flown. The massive engine produced smooth, steady power without the vibration and roughness characteristic of Japanese radials. Controls were heavy but responsive, requiring more physical strength than Zero pilots were accustomed to, but providing precise handling. The cockpit environment differed dramatically from Japanese fighters. Extensive instrumentation provided detailed information about engine condition, fuel state, and aircraft systems. American pilots flew with information. Japanese pilots could only estimate. Electrical systems powered radios, navigation equipment, and weapon systems reliably. Heating systems maintained cockpit temperatures during high-altitude operations. Most importantly, the Corsair climbed with authority that seemed to defy its weight. From sea level to 10,000 feet, climb performance was impressive but not extraordinary. Above 15,000 feet, however, something remarkable happened. While Japanese fighters began losing power as air density decreased, the Corsair maintained strong climb performance through a sophisticated two-stage supercharger system. The supercharger technology was key to understanding American fighter superiority. Japanese engines relied on single-stage superchargers that lost effectiveness at high altitude. American radials like the R-2800 incorporated two-stage systems that automatically shifted to high-ratio gearing as altitude increased, maintaining manifold pressure and engine power where Japanese fighters became increasingly impotent. This technology represented engineering sophistication Japanese industry could not duplicate. Two-stage superchargers required precision manufacturing, advanced metallurgy, sophisticated control systems, and extensive development testing. American aircraft engine manufacturers had invested years and enormous resources developing these systems, creating capabilities. Japanese engineers understood theoretically, but could not produce practically. Kitahata conducted climb tests to 20,000 feet, timing his ascent and comparing results to Zero performance data. The findings were disturbing. From sea level to 10,000 feet, a Zero A6M5 could match or slightly exceed the Corsair's climb rate. Between 10,000 and 15,000 feet, performance was roughly equal. Above 15,000 feet, the Corsair pulled away decisively. At 20,000 feet, the Corsair was climbing at approximately 1,500 feet per minute, while a Zero would struggle to achieve 800 feet per minute. The disparity increased with altitude. At 25,000 feet, the Corsair maintained useful climb performance, while a Zero could barely sustain level flight. These results contradicted everything Japanese aviation believed about fighter performance. Kitahata repeated his tests, suspecting measurement errors. The results remained consistent. The heavy American fighter outclimbed Japan's premier interceptor at precisely the altitudes where combat was increasingly occurring. American bomber formations routinely operated above 20,000 feet, using altitude as protection against Japanese interceptors. If American escort fighters could climb to these altitudes faster than Japanese interceptors, they possessed decisive tactical advantages. They could position themselves above attacking fighters, dive on them with speed and energy advantages, and escape through superior climb performance before Japanese pilots could respond effectively. Lieutenant Commander Horikoshi analyzed the data with growing comprehension. The Americans had solved fundamental problems Japanese aviation hadn't even recognized. High-altitude performance required sophisticated engine technology, 70-stage supercharging, precise fuel metering, advanced metallurgy, and quality control beyond Japanese capabilities. More troubling was the realization that American fighters incorporated these technologies as standard equipment. The Corsair wasn't an experimental prototype or limited production aircraft. It was mass-produced by multiple contractors, with thousands rolling off assembly lines monthly. American industry had solved complex engineering problems and manufactured solutions at scales Japanese planners considered impossible. The psychological impact deepened when Kitahata tested the Corsair's diving characteristics. Japanese pilots reported that American fighters could dive away from combat faster than Zeros could follow, escaping through superior speed rather than maneuverability. The captured Corsair confirmed these reports dramatically. Diving from 20,000 feet, the Corsair accelerated to speeds approaching 500 miles per hour, velocities that would tear a Zero apart. The American fighter's structure was designed for these loads, with massive wing spars and reinforced control surfaces capable of withstanding forces that exceeded Japanese design limits. Japanese fighters were built for different combat conditions. The Zero's legendary maneuverability came from light construction and large control surfaces optimized for low-speed dogfighting. At high speeds, these same characteristics became liabilities. Controls became ineffective, structures approached failure limits, and pilots lost the agility advantages that had made Zeros formidable in early war combat. American fighters reversed these priorities. They accepted reduced low-speed maneuverability in exchange for high-speed handling, structural strength, and power, advantages that dominated combat at medium and high altitudes. The Corsair could absorb battle damage, maintain control at extreme speeds, and climb away from danger using engine power Japanese fighters couldn't match. The testing program expanded through April 1945 as fuel availability permitted. Each flight revealed additional performance advantages that seemed to contradict fundamental assumptions about aircraft design. The Corsair's roll rate, despite its size and weight, exceeded Zero performance at high speeds. Its turning radius, while inferior in slow-speed situations, remained competitive at combat speeds where engagements actually occurred. Most importantly, the American fighter maintained these performance characteristics consistently. Japanese fighters often suffered from control problems, engine difficulties, or system failures that limited their combat effectiveness. The Corsair operated reliably across its entire performance envelope, providing pilots with predictable handling and dependable systems. Captain Kitahata summarized his findings in a technical report that shocked Japanese naval aviation. The Corsair outperformed the Zero in every category except low-speed turning radius and operational range. Speed, climb rate, diving ability, firepower, structural strength, and high-altitude performance all favored the American fighter decisively. Most disturbing was the report's conclusion about American industrial capabilities. The Corsair wasn't extraordinary by American standards. It was representative of routine production. While Japan struggled to build Zeros with increasingly substituted materials and declining quality control, American factories produced superior fighters by the thousands with consistent quality. The implications extended beyond single aircraft comparisons. If American industry could mass-produce fighters superior to Japan's best designs, if American pilots trained extensively in aircraft with decisive performance advantages, if American logistics could support operations across thousands of miles of ocean, then Japan's position was hopeless, regardless of pilot skill or tactical innovation. Japanese aviation had based strategy on assumptions that were fundamentally incorrect. The belief that lightness and maneuverability could overcome power and technology had been disproven by systematic analysis of captured equipment. American fighters weren't winning through numerical superiority alone. They possessed technological advantages that nullified Japanese tactical doctrine. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engine analysis proved most devastating to Japanese assumptions. Lieutenant Commander Horikoshi's detailed examination of the Pratt & Whitney R-2800 revealed manufacturing precision that Japanese industry could not consistently achieve. The 18-cylinder radial engine incorporated technologies Japanese engineers understood theoretically, but could not produce reliably at scale. Each cylinder was machined to tolerances measured in thousandths of an inch, with surface finishes so smooth they appeared almost polished. The pistons, connecting rods, and crankshaft components showed dimensional accuracy that Japanese manufacturing struggled to duplicate, even in laboratory conditions. Most critically, the two-stage supercharger system represented mechanical engineering sophistication beyond Japanese industrial capabilities. The armament installation demonstrated similar technological advantages. 6 Browning 50-caliber machine guns provided overwhelming firepower compared to the Zero's mixed armament of 2 20mm cannons and 2 7.7mm machine guns. American ammunition capacity totaled 2,350 rounds, compared to approximately 1,000 rounds in Japanese fighters. More importantly, American weapons were manufactured to standards, ensuring reliable function under combat conditions. Japanese aviation increasingly struggled with ammunition quality, weapon reliability, and maintenance support as industrial capabilities deteriorated. American pilots could fire their weapons confidently, knowing they would function as designed. Japanese pilots increasingly encountered misfires, jams, and ammunition failures that compromised combat effectiveness. The fuel system analysis revealed sophisticated engineering Japanese designers admired but could not duplicate. Self-sealing fuel tanks incorporated multiple rubber layers that swelled when punctured, preventing catastrophic fuel loss from battle damage. Japanese fighters largely lacked this protection, making them vulnerable to incendiary ammunition that could destroy aircraft with single hits. American fuel systems also incorporated advanced pumps, filters, and flow controls that maintained engine operation under extreme flight conditions. Japanese fighters often experienced fuel flow problems during violent maneuvering, limiting pilot options during combat. The Corsair's systems functioned reliably regardless of aircraft attitude or G-forces, providing pilots with consistent engine performance throughout engagement envelopes. Perhaps most revealing was the overall systems integration. Every component in the Corsair was designed to work harmoniously with every other component. Electrical systems powered extensive equipment through high-quality wiring with proper insulation and organization. Hydraulic systems operated landing gear, wing-folding mechanisms, and propeller controls with reliable precision. Engine controls provided smooth power management across all operating conditions. Japanese fighters increasingly suffered from system incompatibilities, as wartime shortages forced use of substitute components not designed to work together. Electrical problems, hydraulic failures, and control system malfunctions became routine occurrences that American pilots rarely experienced. The technological gap wasn't limited to individual components. It encompassed entire systems engineering approaches. The psychological impact on Japanese test personnel deepened as analysis continued through April and May 1945. Every system examined revealed American technological sophistication exceeding Japanese capabilities. The cumulative effect created recognition that Japan was fighting enemies possessing decisive advantages in every category that mattered for modern aerial warfare. By June 1945, Japanese fighter strength had been reduced to fewer than 2,000 operational aircraft, many flown by inexperienced pilots with minimal training due to fuel shortages. American carrier forces operated off Japanese coasts with virtual impunity, their fighters sweeping remaining Japanese aircraft from the sky in one-sided encounters that resembled training, exercises more than combat. The examination of the captured Corsair concluded in July 1945, when American forces overran the test facility. Japanese engineers had completed their analysis, documenting every system, measuring every component, understanding precisely what technologies their nation lacked. The knowledge came too late to influence the war's outcome, but would shape post-war reconstruction profoundly. When Japan rebuilt its aerospace industry under American guidance during the occupation, former military engineers applied lessons learned from examining American technology. The emphasis shifted from pursuing lightness and simplicity to incorporating sophisticated systems and advanced manufacturing techniques that characterized successful American designs. The transformation extended beyond aviation. Japanese automotive, electronics, and precision manufacturing industries adopted quality control standards and systematic engineering approaches, inspired partly by recognition of American technological capabilities during the war. The shock of discovering superior enemy technology motivated post-war emphasis on matching and eventually exceeding foreign capabilities. Captain Kitahata survived the war and later worked with American occupation forces, sharing expertise in Japanese aviation development while learning American engineering and manufacturing techniques. He never forgot flights in the captured Corsair or the realization that Japan had been fighting with obsolete equipment against technologically superior opponents. The story of Japanese pilots examining the captured Corsair and refusing to believe its climb performance illustrates how technological surprise can transform understanding. Initial disbelief gave way to systematic analysis, which revealed capabilities that shattered fundamental assumptions about aerial warfare. The mathematics were undeniable. The Corsair outclimbed the Zero at operationally critical altitudes through sophisticated engineering Japanese industry could not duplicate. American fighters possessed decisive advantages that made engagement outcomes predictable regardless of pilot skill or tactical innovation. Recognition of these advantages came too late to change the war's outcome, but influenced the peace that followed. Japanese aviation rebuilt itself based on lessons learned through painful confrontation with superior technology. The emphasis shifted from traditional priorities to capabilities that determined success in modern technological competition. The captured Corsair served as more than an intelligence-gathering opportunity. It became a teacher that demonstrated the cost of technological complacency and institutional resistance to change. Japanese engineers learned that advanced engineering, superior manufacturing, and systematic development created advantages that courage and skill alone could not overcome. These lessons influenced Japanese industrial development for generations, shaping approaches to quality, innovation, and technological competition that characterized the nation's post-war economic transformation. The psychological impact on Japanese aviation personnel extended far beyond the immediate technical revelations. For engineers like Horikoshi, who had dedicated their careers to pursuing efficiency through weight reduction and simplification, the Corsair demonstrated that their fundamental assumptions about successful fighter design were not merely inadequate, but counterproductive in modern aerial warfare. The realization that American designers had solved problems Japanese aviation had not even recognized represented a form of technological shock that transformed understanding at the deepest level. The institutional implications were equally profound. Japanese aviation had organized itself around design philosophies and manufacturing approaches that produced impressive individual achievements, but could not compete with systematic American advantages in every category. The Zero remained a remarkable aircraft by any objective measure. Its range, maneuverability, and climb performance at low altitudes were genuinely exceptional. However, these qualities had become irrelevant when confronted with opponents possessing decisive advantages in the performance areas that actually determined combat outcomes. American pilots flying Corsairs, Hellcats, Mustangs, and Thunderbolts operated from positions of technological superiority so complete that individual skill differences became secondary considerations. Superior climb rates, diving speeds, structural strength, firepower, and systems reliability created nearly insurmountable advantages that made engagement outcomes predictable regardless of pilot experience or tactical innovation. Japanese aviators, regardless of their courage and dedication, were fighting with obsolete equipment against forces equipped with the products of superior industrial and technological systems. The lessons learned through examination of the captured Corsair influenced Japanese strategic thinking far beyond aviation. Recognition that technological competition determined outcomes in modern warfare shaped post-war defense policy, industrial development, and international relations for decades. Rather than pursuing independent development paths likely to fail against superior opponents, Japan chose to align with technological leaders and focus resources on matching capabilities rather than challenging them directly. The transformation was visible in multiple industries, as former military engineers applied wartime lessons to civilian production. Companies like Sony, Toyota, Honda, and Canon recruited personnel who understood the importance of quality, precision manufacturing, and systematic approaches to complex problems. The emphasis on continuous improvement, statistical quality control, and integrated systems design that characterized Japanese industrial success traced directly to recognition of American capabilities during the war. When Japan rebuilt its aerospace industry under American guidance during the occupation period, the captured Corsair's lessons were fundamental to new approaches. Former Zero designer Horikoshi worked on civilian aircraft projects, applying insights gained through painful examination of superior American technology. The emphasis shifted from pursuing traditional Japanese priorities to incorporating sophisticated systems and advanced manufacturing techniques that enabled competitive performance against international standards. By the 1970s, Japanese aviation companies were producing aircraft that incorporated American technology and design philosophy learned through systematic study of captured equipment. The T-2 trainer and F-1 fighter demonstrated Japan's ability to create modern aircraft using lessons learned about the importance of advanced engines, sophisticated systems, and comprehensive integration of multiple technologies into cohesive designs. The captured Corsair represented a watershed moment when one nation's technical establishment confronted another's decisive advantages and acknowledged the implications with scientific honesty. The careful analysis, precise measurements, and detailed assessments revealed engineering minds forced to confront uncomfortable truths about their nation's capabilities and fundamental assumptions about technological competition. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.